Okay, so after going through all of that mess and a lot of struggle, is there an easier way? And the answer is yes. So there is a shortcut to some of it, some problems, not all of them. But this is what we call the divergence theorem. So the divergence theorem is the following. So let E be a simple closed solid region, and S is the boundary surface of E with positive orientation. So let F be the vector field whose components have continuous first partial derivatives. Then, if I want to find F dot ds, which is basically the flux, all you just have to do is take the divergence of dV. Now, what exactly is divergence? So the divergence of F is just the addition of all the partial derivatives. This is very similar to the curl, but the curl is basically looking about the circulation. The flux is basically how is a vector field behaving towards or away from a point. So if the vector field represents the velocity of the fluid, then the divergence of the vector field at a point is the net rate of change with respect to time and the amount of fluid flowing away from P. So if the amount of fluid is the same as the amount of fluid going in and is the same as the amount flowing out, then the divergence is 0. Okay, so what we're going to do is we're going to use the divergence theorem using this problem. So this problem should be very familiar to you. It was this terrible problem, right? So where we got our answer to be 5 pi over 2. And notice that we need to look at all 3 different sides to find the total flux. Okay, so let me go ahead and show you that the answer was 5 pi over 2. Just got cut off. So now what we're going to do the same problem, but now using the divergence theorem. Okay, so the only thing that you have to be very careful is that with the divergence theorem, in order for you to use it, the region has to be closed. So for example, the problem that we just did in the previous video, this one's not closed. This is open. We're just looking at the flux within this within the outside of the cylinder. There's no flux here, no flux here. We're not treating this as a closed surface. So we need to be very careful. The way that I will let you know if this is that you are going to be able to use the divergence theorem, I will tell you that if it's closed or not. Okay, so let's go ahead and do this example. So why did it freeze? Let's check. So, okay. So just to remind you, we want to find the flux using the divergence theorem. And here the surfaces consist of all 3 surfaces, top, sides, and bottom. Okay, so this is a closed surface, right? Because you have all these 3 different components. So let's find the flux using the divergence theorem. So we're not going to worry about the normal vector. We're not going to look at all of the 3 things. What we're going to do instead is do this triple integral and take it over the divergence. So I'm going to take the triple integral. So our flux is going to be equal to the triple integral over the region E of the divergence of F. So let's start off with the divergence. So the divergence is just going to be the partial derivatives of each of them. So partial P over X, partial Q over Y, and partial R over Z. So partial P of X, that guy is just going to give me Y. Partial Q, that's going to give me negative Y. Partial R over Z is going to give me 1. You can see that the divergence is going to be equal to 1. So all I got to do is take the triple integral of 1 dV. Okay, this seems like a pretty good integral. All right, now we need to go ahead and take a look at the region. So if you remember, you have a paraboloid going up at 4, going downward. Then you have our cylinder from 0 to 1. And then you got the bottom part as z equals 0. Okay, so now if you take a look at this guy, let's look at our z component. So our z component is going from 0 all the way to the paraboloid. So z is going from 0 all the way to the paraboloid. Let's convert this to cylindrical coordinates, actually. This would be really nice if I do cylindrical. So this will be 4 minus 3r squared. Now let's take a look at the radius. Well, the radius is just going to be from 0 to 1, right? Because if you take a look at that, it's going to be from 0 to 1. It's a circle from 0 all the way to 1. And then our theta value will just be from 0 to 2 pi. So we're going to get from 0 to 4 minus 3r squared, 0 to 1, and 0 to 2 pi. Divergence is 1, and then this is going to be dz, dr, d theta. And because we have converted to cylindrical, we need to make sure that we multiply by r. So first, let's go ahead and take the antiderivative with respect to z. So we're going to get 0 to 2 pi, 0 to 1, rz from 0 to 4 minus 3r squared, dr d theta. Then we're going to have the r, that's going to be 4r minus 3r cubed, dr d theta. We're going to take the antiderivative with respect to r now. So it's going to be 4r squared, so 2r squared minus 3/4 r to the 4th from 0 to 1, d theta. So that should give me what? 5/4. So it's going to be 5/4 theta, which gives me 5/2 pi. Oh, which is exactly the same thing as before, but with a lot less work. So at the very end, this really simplified a lot of the work. Again, what we really need to make sure is that there is our region itself, our entire region and our entire solid is closed. So I do have some more problems on divergence theorem. I'll go ahead and post them on our Canvas shell, or you can see them in my YouTube channel as well.